Welcome WE23 to the today's lecture of the course of microcontrollers. For today's lecture, we are going to follow the chapter 2 of the book by Muhammad Ali Mazidi. In today's lecture, we will study about different status registers. We will also discuss how we can instruct a microcontroller using the assembly language, and we will also discuss the particular format or the syntax in which we can lay down the instructions. At the end of today's lecture, we will be able to understand how we can access different flight registers of the microcontroller and how we can perform different arithmetic logical operations using the working register and different instructions. And we will try to solve some simple problems to understand it better. The first register we are going to study is the working register. Working register in general, like all registers, is used to store information. The difference is that this register is used to perform the arithmetic logical operations that can be performed by the microcontroller. And this is the only one register. This represents the layout of the working register, which is labeled, which can store 8 binary values. This means this working register is 8-bit wide, and the first value starts from the bit D0 and it goes to D7. The PIC microcontroller follows the little endian format. This means that the, the bit on the extreme right is the LSB, means it represents the least significant information, and the bit on the left represents the MSB, which is the most significant bit and represents the most significant information of this register. If we have to place some value in this register, we need some instruction set that can move the data from one place to another place, from like the file registers to the working registers, and from the working register to the file registers in the assembly language. The first instruction that we are going to discuss is the move LW. Um, the general way to read any instruction is that the instruction is composed of the mnemonic and then the operands. In this case, the mnemonic is the MOV, which means move something, and the operands are the literal values in the working register. The literal value means the number itself. So this instruction means that we are going to move a literal value to the working register. So this is the mnemonic which represents the move, and this represents the operands on which this instruction is going to be applied. Here L represents the literal value, and W represents the working register. So width of this working register is 8-bit, as we discussed earlier. So in this case, this move command can move a total of 8 bits at any given time. Let's see a few examples. In the first example, we are going to move a value 25H into the working register. So let's say this is the configuration or the state of the working register before the execution of this command. Once this instruction gets executed, the literal value 25 will be moved to the working register, and here H represents hexadecimal format. So currently, if we look at the working register has slot for 8 bits. This is D0, 1, 2, 3, 4, 5, 6, and D7. So since this is a kind of a still high level language, but the compiler will convert this into the binary language to be processed by the microcontroller. So this can be represented as 0101, and then 2 can be represented as 0010. So this is how the binary bits will be occupying the working register. Similarly, in the second case, the literal value A5 will be moved to the working register. So in this case, since the working register is already occupied by the 25, unless we save this value and if the next instruction is executed, the previous value will be replaced by the new value and we will lose the previous information. So we have to take care. If we want to save some information, we have to move this information out of the working register, most likely to the sum of the available file registers, and then perform the next information. Next, we have some more commands, and let's see what is wrong with them. So move LW9H, it seems technically right because we have a 8-bit space, and 9H is can fit perfectly within the 8 bits. So there is no error, but there are sometimes there are compilers which throw errors because of the formatting of this number. Usually the compiler accepts two numbers, 09H, then the compiler will not throw any error. So it depends upon the compiler, and in some compilers even this is a valid instruction, and what the compiler will do, it will automatically fill up the MSBs with the zeros. So when the compiler will read 9H, and this is a valid instruction for the particular version of that compiler, it will automatically fill the MSBs with the 4 zeros, and it will place 1001 in the LSB to represent 9. How about the next instruction, move LW823H? With respect to appearance, this seems to be a valid command because the syntax is valid. The move LW is followed by a literal value, but the thing is, since these are the hexadecimal values, and in hexadecimal format each number is represented by 4 bits. So in this case, the first 4 bits will be occupied by 3, next 4 bits will be occupied by the number 2, and there is no space to store A. So there are two options that can happen after the execution of this instruction. First possible way out is that the compiler will throw an error and the execution will stop. And the second way out is that the compiler will throw away some of the information and fit rest of the 8 bits. So what really happens in the PIC microcontroller, this is a valid command, so it will not throw an error, and the second option will occur, that it will throw away the MSB, and the working register will be filled by the value 23H. The next instruction that we are going to study is the addition instruction. Again, how to read it. The first is a mnemonic to perform add, and then these are the two operands on which the instruction is going to be performed. This instruction add LW, add two values. The one value is the literal value, and the one value will be from the working register. So let's see some examples. Uh, let's say this is the initial state of the working register. So in this case, the working register is empty. So what we are going to do is first we have to use the move command, move LW, and this instruction will do move this literal value to 12H to the working register WREG. And now we are going to perform the next instruction, add LW16H. So now what is going to happen? Unlike the move command, which replaces the older value, the add command performs the following action: W goes to W plus K, where K is the literal value provided and W is the existing value of the working register. And sorry, this is the direction of the arrow. After this sum is performed, the working register will be updated with this new value of the sum. Similarly, in the sequence, we have performed two more addition operations. In each case, we are adding new value. So finally, the working register is going to have only one single value that will represent sum of all these values. So far, we have discussed two commands. First one was the move LW, and second one was the add LW. If you look at the hardware circuitry that is going to perform these operations, then it is represented by this figure. It shows us that so far we are not using any external registers. All we are using is the arithmetic logical unit, and then we have the working register, and the information is flowing in such a way that the literal value comes to the ALU, and the information from the ALU follows the working register. If the output of the working register is again moved back to the ALU, then we can see there is a status register connected with the ALU, which can provide us different kind of information based on the available flags, which we will discuss later. Next, we have the PIC file registers. PIC file registers are also known as data RAM. They are used for storing information that can be coming from during the execution of the instructions, or this is the information that is already provided for the program. Then this information is generally stored in the general purpose RAM. Then we have the special function registers. Special function registers are provided by the designer and their functionality is fixed, which cannot be changed during the execution of the program. For example, there can be input output registers, there can be timers, and there can be uh, ADC, analog to digital converter registers. So their functionality is pretty much fixed as compared to the general purpose registers. Uh, Moreover, the general purpose RAM can be further divided again into two categories. First one is the GP RAM, and the second one is the EEPROM, which is electrically erasable programmable ROM. The GP RAM is part of the microcontroller. Irrespective of the size, like different microcontrollers have different amount of general purpose RAM, but it is always there. In contrast to the EEPROM, which is an external aid, and there is a possibility that a microcontroller has some amount of GP RAM, but there is a zero EEPROM. Irrespective of the amount of the memory, all of these registers are 8-bit wide. This is the graphical instruction. What we have studied so far, we have an ALU that is connected with the working register and with the data bus. And the data bus provides the interface between the file registers, which can store a large amount of information as compared to the working register, which is only one and can store only 8 bits at a time. We studied some instructions which were following some this kind of syntax where there is an operation code, then this is the binary overall packet that is moved in each cycle, where D represents the result destination, A represents the state of the SS bank, which we are going to study in a while, and then the final part of this instruction represents the second address of the second operand. There are a few properties about this illustration. First one is that all the instruction sets are orthogonal. This means that all the memory locations are uniquely addressable and there is no overlap between the addressable memory. As we discussed, registers can be classified into general purpose registers and the special function registers. These are the set of the special function registers that are available, including the input-output registers, the interrupts, the EEP, PROM registers, serial input-output timers, and so on. Then we have already discussed the registers available with the ALU. This is the working register, instruction decoder, status registers. Then there is a bank select register. Then we discussed the program counter in the stack pointer. There is another table pointer that we are going to discuss soon. The special function registers are 8-bit registers, and the number of these registers vary from one model to another model. And then we have the general purpose registers or the general purpose RAM. General purpose RAM is usually much more than the special function registers, and also uh, it's a bit difficult to access a large amount of RAM because we need a large amount of addressable memory, which makes it difficult for the microcontroller because of limited set of uh, address lines. Therefore, we use some special routines in the C compiler to address a larger amount of size. And we will study also the bank select registers that are used for this purpose. Here we can see the file register size of different models of the microcontroller. We can see that the largest memories available is on PIC 8772, which is 4096 bytes, and the file registers memory is divided further into two portions, as we know. One is the SFR, special function registers, and the general purpose RAM. And we can see that most of the microcontrollers have a PIC microcontrollers have a 256 bytes of special function registers, and some of them have other amounts of RAM. And but in contrast, the general purpose RAM is highly variable, and every microcontroller has a different size of general purpose RAM. Here we can see the addressing configuration of different microcontrollers. In the earlier versions of the microcontrollers, the SFRs are assigned the address space from the starting values, followed by the GPU RAMs. However, in the PIC-18F, this trend got changed, and now the SFRs are placed at the bottom, and the GPU RAMs are allocated the initial address space. This is a detailed memory map of the file registers. Here we can see that we have 15 banks, and each bank is of 256 bytes. Moreover, we can see that the special function register is further divided into two parts, and half of it is unused and rest of the 128 bytes are assigned to the special function registers. And also we can see that the first bank, that is bank 0, is also divided into half, this is also 128 bytes. For the faster access, there is a bank known as the SS bank. SS bank is composed of 128 bytes of GP RAM and 128 bytes of the SFRs. So because the memory address range is quite large from 00H to 000H to triple FFH, in this case, the addressing scheme is quite complex. So in order to provide a faster access to the microcontroller, and this access bank is designed. And this is used for the default memory operations. If more memory is required, then special bank select register is used to select different portions of this file registers using some additional circuitry. However, we can use it, but for the faster access, we use the access bank. As we discussed earlier, the access bank is constituted by concatenating part of the general purpose RAM and part of the special function register, where each of the subdivision is of 128 bytes. The GP RAM is assigned the addressing from the beginning from 0 to 7FH, and the special function register, since it's placed at the very bottom of the file registers, is assigned addresses that are at the very end of their addressable space. These are the registers that are the special function registers available on the PIC18F. You can see there are huge numbers starting from port A, B, C, D, E, storing for used for storing data. Then we have like all sort of registers, like there is a bank select register. Then we have the table latch and the table pointers. So we will study the functionality of these registers throughout the course. Now we are going to discuss some of the instructions that can be executed without using the different banks and only using the default bank, that is the access bank. These commands include the move WF. The first command is the move WF. The nomenclature is the same. The first part of the instruction represents the action that is going to be performed, that is moving the information from one place to another, and the two operands involve the working register and the file register that are both part of the access bank. Here the F indicates the file register and what is the direction of information flow. So here the working register is the source and the file register is the destination. So we are going to move the information from the working register to a destination in the file register. And so there are, in the access bank, the file register is of 128 bytes, and we know that each memory slot is of 8 bits. This means we have to further specify the address where this information is going to be stored. So both the working register and the file register are of the same bit width, that is of 8 bits. So in this command, beside this instruction, we have the information of the address, which will specify the particular location where the information is going to be stored. Let's see an example. We will write, let's say, move WF, let's say 00H. So after the execution of this instruction, whatever the content of the working register are will be moved to this particular location. Here is another example involving two instructions, move LW, which is for moving the literal to the working register, and the other instruction that we just discussed is the move WF, which is used for moving the values from the working register to the file registers. So in this example, when the first instruction will be executed, the value, the literal value 99H will be placed into the working register. This is after the first instruction is executed. What is the second instruction? In the second instruction, the working register information is moved to the file register, and where in the file register the address location is 12H. This means this information will now be moved to the address 12H. So 99 is placed at this address. Same, the sequence of instructions continues at each uh, pair of instructions. After each pair of instructions, we are providing a new literal value, and that is moved to the file register with a different address. So we have provided in this example uh, 5 different literal values ranging from 99, 85, 3F, 63, and 12, and these values are sequentially moved from the working register to the file register to be used later in the program. In the previous slide, we have sequentially executed two set of instructions. One was to move literal value to the working register, and the other instruction was to move the information in the working register to the file register, and this instruction set is followed by the address. Someone might argue that why we cannot move the values directly to the file register. However, in PIC in order to perform operations, we must move the information to the working register first, and then from the working register we can move the information to the file register. That's why this is not possible in this specific microcontroller.